Hello and welcome back. In this video, we are going to look at reciprocal basis vectors. In the previous video, we looked at vector expansion, and in that case, the main idea was that the basis vectors were orthogonal to each other. So, if we had two basis vectors s1, s2, they were orthogonal. But what happens if we have basis vectors, let's say v1, v2, that are not orthogonal to each other, right? So, if this is the case, then how do we perform the vector expansion, because the general formula that we looked at in previous video does not work here. So let's go through one example and hopefully this will make things clear. If we have a vector x which is 0, 1.5, and uh, if we assume that uh, this is based on orthogonal basis vectors such as s1 is equal to 1 0, s2 is equal to 0 1, then these are orthogonal, and we can see that right here in the plot. The s1 and s2, 1 0 and 0 1, they are orthogonal, and so the vector expansion, in this case we could simply write x of s is equal to uh, this would be 0 s1 plus 1.5 s2. And so here what we are essentially saying is that the coefficients of the equation. So if you remember, the equation we would write would be something like this: x1 s1 plus x2 s2, right? So the coefficients x1 and x2 are simply these. So x1 is 0, x2 is 1.5, and that works pretty good if we know that the basis vectors are orthogonal to each other. Now let's try and see what happens if the basis vectors that we have are not orthogonal. So if they are not orthogonal, then we have some different values. So let's assume that those vectors are as follows: v1, which is 2 1, and the other vector v2 s, that is equal to 1 2. And we can plot these, and here in the plot we can see that that's the v1 vector, that's the v2, and obviously, as you can see, they are not at 90 degrees to each other. There's and these red arrows that we see here on the screen. So how do we then use those vectors as basis vectors to represent this particular vector x, and what coefficients would we have to use? And that is what we are going to look at in this video. In general, if we try to think about applying the regular expansion where the basis vectors are orthogonal, one problem with that is if we look at the dot product of v1 with v2, the dot product is going to be, let's say, 2 1, and then we have 1 2. What we get is 2 times 1 is 2, 1 times 2 is 2, and we get a value of 4. So this obviously is not equal to 0, which is telling us that v1 of s and v2 of s is not perpendicular. So the is not perpendicular, right? Perpendicular, or they are not orthogonal. And so the simple projection formula that we have looked at, which is x of j is equal to, take the dot product of v of j with x and divide that by v of j, so the norm of squared norm of v of j, vj. So this won't work. This won't work here, and therefore the idea is to introduce something called as a reciprocal basis vector. So we are introducing something called as a reciprocal basis vectors, and it is what the name suggests. So let's look at this now. So what we have, let's say we define a new set of vectors r1, r2, such that if we dot this r, any r with the v's, then we get a 0 if the I is not equal to j. That is, of course, you are not dotting it with itself. R is, if we dot r with r1 with v2, r r1 with v, any other value that is not I, then we get a 0. So if we dot r1 with v2, we should get a value of 0. That is to say that they would be perpendicular or orthogonal. In other case, we get a value of 1. And so with this idea, what we can now do is take our equation that we have, which is the x of x is equal to, and previously what we said that this was equal to x1 v1 plus x2 v2. Now what we do is dot this with r of j, and what we get is rj dotted with x is equal to this, we dot this side, so what we get is rj dotted, so we get x1 x1 v1, so that should be v1, and then we get plus rj, and this would be uh, x x1, so this would be x2 v2, and as we, so yep, then we can move things around, and what this would get us is we get the x1 out, and then we have rj dotted with v1, and then we have x2 rj dotted with v2, and based on the equation, the assumption that we have above, we can clearly see that uh, if uh, if uh, if we have a condition where I is not equal to j, then uh, the dot product would be 0, and therefore what we are left with is just x of j, and so what we are saying is r of j is equal to rj dotted with x is equal to simply x of j. And why is that the case? Because here, let's say we replace the j with 1, what we have is r1 x is equal to r, this is going to be x1 r1 comma v1 plus x2 r2 comma v r2 comma v2, so that's a comma because we are doing a dot product, so this should be a comma. And so what remains here is, so by definition that we have above, r1 v2, wherever we have this number right here and this number right here, they don't match, then it has to be 0. So this is equal to 0. Likewise, we have let's write here R1 V3, that would be 0. We have R1, any of the uh, V values that we have here, those would be, let's say we put uh, V of j, those would be all 0, except when the j is not equal to 1. So to keep things simple, let's not write that. And so what we are left with is only one case where we have R1 V1, that is when we have the value as 1. And what that translates to is that x of x1 is equal to R1 x, and that's sort of the coefficient of the expansion, and that's what we are trying to say here. That is, the x of j is equal to r of j, then r of jx. So that is the same thing as what we have here. And then the idea here is that if we try and expand this x that we have using the vectors, basis vectors v1 v2 that are not orthogonal to each other, then we can do that as follows. We take the values for v1 and v2 and put them in a matrix B. So the values of v1 we have are 2 1 and 1 2, so we can put them in a matrix B, 2 1 and 1 2, so that is our v1, that is our v2 that we have. So here what we are trying to essentially do is create this particular matrix B, which is made up of several of these vectors, basis vectors v1 v2 all the way up to vn. And we also uh, then think about reciprocal basis vectors R, which are R1, R2 all the way up to Rn. And then here we can represent their dot product as R of I comma V of j is equal to so that those are the individual values, and here this is the matrix R transpose I and dotted with V of j. So these are the bold letters R and V, and we can write it in a matrix form as R transpose B, and that is equal to I, which is the identity matrix. And here this B is what we have here and the R is what we have here. So if we bring B to the other side, what we get is R transpose is equal to B inverse. We can say that the matrix of reciprocal basis vectors when transposed is exactly the inverse of the matrix formed by the original basis vectors here in B. And so here if we take transpose of both the sides, we get R is equal to B inverse transpose. So what this means is we can find the reciprocal basis vector simply by taking the inverse of the basis matrix B and then transposing it. So each column of this new matrix R will be one of the reciprocal basis vectors Ri that we are looking for in here. So let's now look at the actual calculation that will go into the example B that we have on the left hand side. So what we are saying here is that if we take the inverse, so if let's take the blue. And here if we compute the B inverse, what we get is minus 1 by 3. So to get the inverse, if you are not already familiar with it, what we need to do is get the determinant. So let's do that first. What we can do is get the determinant of B, and that is equal to 2 times 2. So this way and this way we multiply. So 2 times 2 is 4, minus 1 times 1, so that is 4 minus 1, we get value of 3. And so the B inverse then is 1 by determinant of B, and here we flip the signs of the diagonals. This is minus 1 minus 1. So what we get in the output is 1 by 3 times 2 minus 1 minus 1 2, which is equal to let's say this is going to be 2 by 3 minus 1 by 3 minus 1 by 3 and 2 by 3. So that is the inverse of B, and what we can now do is compute the coordinates. X is equal to 1 by 3, so that we already have that. So what I'm going to do is instead write the entire thing, 2 by 3 minus 1 by 3 minus 1 by 3 2 by 3, and here we have the x, which is 0 1.5, and so this dot product would be so this would be 2 by 3 times 0 is 0, minus 1 by 3 times 1.5 is minus 0.5. Minus 1 by 3 times 0 is 0, and 2 by 3 times 1.5 is 2 times 0.5, that is just 1. And so the value we get for this x is 1. So these are the coefficients. Now what we can do is take these coefficients and put them in our equation for x. So what we are saying here is that this is x1, this is x2, and so when we look at our equation x, vector x, if we expand it in terms of v1 and v2, then these are the coefficients it would need: 0.5 for x1 and 1 for x2. So this is the same thing as saying x1 v1 plus x2 v2. It's just that we now have the coefficients, actual values for x1 and x2. So that's the expansion of the vector x1 based on the basis vectors that are not orthogonal. Now you're probably saying, hey, where is the r? We haven't used the r anywhere. So let's try and look at that now. So the r is going to be the transpose of this, and so what we have is, in this case it's just going to be the same. If we look at 1 by 3, if we transpose that, it would still be uh, 2 minus 1 minus 1 2, because this is a symmetric matrix, and so r1 is equal to 2 by 3 minus 1 by 3, r2 is equal to minus 1 by 3 2 by 3, and if we now uh, compute the coefficients by inner products, let's say r1 and x, so this would be 2, so this, let's write it like this: 2 by 3 minus 1 by 3, dotted that with x, and x, as we know, is 0 1.5. So this gets us a value of 2 by 3 times 0 is 0, 1 by 3 times 1.5 is uh, minus, so this is 2 minus 1 by 3 times 1.5, and that is 0.5, and that gets us minus 0.5. And if we dot R2 with x, we have this vector minus 1 by 3, 2 by 3, and here we have the same x 0, 1.5, and in the output then what we have, this would be 0 minus 1 by 3 times 0 is 0. Then what we are left with is 2 by 3 times 1.5, and that is simply, this is 3, this is 0.5, and 0.5 times 2 is simply 1. And so what we have are these two coefficients again, x1 and x2. Again, these are the same. So these are the same that we have here, x1 and x2. So what we are saying is that, let's change the ink. What we are saying is that R transpose B is equal to B inverse B, which is equal to I. And so that is what this particular video was about, where we talked about vector expansion, where the two vectors are not orthogonal, as you can see. And just to complete the discussion, here we have these blue arrows. What this blue arrow is uh, scaling of the vector v1. So here we are saying that we need to scale the vector v1 by minus 0.5, as we see here. So we divide it by 2 and add a negative sign to it. So this vector v1, we divide it by 2, add a negative sign to it, and so that's the scaled version of v1. And for the vector v2, it stays the same. So we just move that vector v2 to the head. So the tail of vector v2 is at the head of the scaled vector v1 right here. And why do we do that? That's because if we want to perform addition, which we do here, minus 0.5 v1 plus 1 times v2, to perform that addition, vector addition, we need to have the tail of this vector v2 on the head of vector v1. And if we do that, we see that it accurately points to 1.5 on the y-axis, which is the vector head of the vector x, and that is what we have here. So this sort of completes the story, that the scaled uh, version of the original vectors v1, that is to say that when we have the coefficients for v1 and v2 that scale it, if we add those scaled values, then we get our original vector x back. Now, just to clarify things a bit here, when we are taking the inverse of a matrix, I just wanted to mention that here are the actual steps. If we have a matrix A with values A, B, C, D, and we are trying to get the inverse of this matrix A, what we would do is get the determinant and then get the inverse of that. So this would be determinant of A would be A times D. So let's write that here, A times D minus B times C. And that's what I'm writing here, A times D minus B times C. And then in here, we would rearrange the values such that D, A, so we are sort of switching these around, and then we are changing the values along the off diagonals as we do here. So in this matrix which we have, where we have uh, these values, let's say 2 along the diagonals minus 1 along the off diagonals, uh, what we have is A is equal to 2, B is equal to 1, C is equal to 1, D is equal to 2. And so the determinant in this case of if we had A, which is this one, determinant of A would be A times D minus B times C, which is equal to 2 times 2 minus 1 times 1, that is equal to 4 minus 1, that is equal to 3. And uh, then here we see that the determinant is not equal to 0, and so the matrix is invertible. So determinant of A is not equal to 0, which is good, and so the matrix, we can invert it, is invertible. And so now when we uh, perform the matrix inversion, here is what we do. A is equal to 1 by 3, why 3, because that's the determinant we found, and then we use this particular uh, matrix that we wrote earlier. So the values would be 2, 2, minus 1, minus 1, and if we write it out, the inverted, so this is A inverse, and so the inverted matrix would be 2 by 3, here minus 1 by 3, and this would be minus 1 by 3, and this would be 2 by 3. And this sort of brings us back to what we have here. So that was it for this video on vector expansion using non-orthogonal basis vectors. And this is also the end of this particular section where we talk about signal and weight vector spaces. I hope this section has been helpful to you, and if you have any questions, comments, or suggestions, please do let me know in the comment section below as we move into the next section in this particular series. Again, if you can share this video with your colleagues, friends who are interested in learning neural network design, it will not only help them learn the topic, but it will also help get more support for this channel to continue, and it will help me continue making more videos for you all. Thank you, and see you in the next video. Bye for now.